just let's recap that real quick. So what is a vector space? Well, it's got to be a set of objects that we're going to call vectors that live over a field. We'll discuss that more a little bit on the next page, together with two operations. Both of these operations have to be closed, meaning when I do vector addition to two vectors, I need to get a new vector. Okay, so the odd numbers were an example of something where that didn't happen. And when I do a scalar and multiply it to a vector, I need to again get another vector. Notice that when I took the even numbers, if I took 1/2 times 6, I did not get another even number. So the even numbers are not closed under scalar multiplication. Additionally, what I mean by vector addition has to satisfy these four properties. That there's something that behaves like 0, and once I know what 0 is, every vector has its opposite, so when I combine them together, I get the combine a vector with its opposite, I get the 0 vector. And we have to have the associative property of addition and a commutative property of addition. As long as I can come up with some operation, I can label it plus. As long as it satisfies these, then I've got something that will behave like addition in my vector space. Okay. Then we have to have our four scalar product properties. Okay. So the first one is that there exists. Oops, I'm sorry. This is not an existence because we've already got the 1 that lives in the field. So for whatever number behaves like 1 in the field, we have that 1 times the vector through scalar multiplication. 1 times the vector v is just again the vector v. Multiplying the vector v by a factor of 1 does not change it. Okay. Additionally, if I took some other scalar alpha and multiplied it to v plus w, let's do u plus v, just keeping with alphabetical order there. If we did it, multiplied it to the sum of u and v, we get alpha u plus alpha v. Okay? We have another, so this is a sort of distributive property. We have another distributive property that says if I took alpha plus beta and multiplied the result of that sum to a vector u, that I would get the same thing as alpha times vector u plus beta times vector u. Okay. So we've got these two different distributive properties. And the last one is an associative property. If I have alpha times beta times vector u, that's the same thing as taking alpha times beta times vector u. Okay. So this is an identity property of scalar multiplication. Sorry, this is the identity property of scalar multiplication. This is the distributive property of scalar multiplication over vector addition. Over addition. Okay. So here we've got vector addition, and what am I allowed to do with it? I'm allowed to distribute the operation of scalar multiplication over it. That's different than this one here, where I've got the distributive property of scalar multiplication over scalar addition. Okay. Folks, I've been trying to be somewhat careful with my wording here. This operation addition here is vector addition. This operation of addition right here is scalar addition. We're adding two scalars here. Here the objects are vectors. So the first distributive property is scalar multiplication over vector addition, whereas this property is the distributive property of the operation here is scalar multiplication, but it's over scalar addition. So notice the difference. I should have said vector addition. So let me change that to say vector addition. Okay, that's a whole lot of properties. This is getting rather long. Let's look at a couple of quick consequences of these properties. You might think that we needed to state these as properties, but it turns out you can prove them from the other two. And that is if we take the number 0, okay, careful, that's the number 0 in the field. Okay? So if I take the number 0 and scalar multiply it to any vector, what I get is the 0 vector. So pay attention here to the difference. If I put a 0 without a line over it, I'm just talking about the number 0, like you're familiar with in the real numbers or in the complex numbers, and I'm scalar multiplying it to some vector, but the result of multiplying any vector by the number 0 gives me the 0 vector. Okay, so that's one property. And another property is that if I take the opposite of any vector, okay, so that's the negative u vector, that's the same thing as -1 scalar multiplied, so I'm going to emphasize that dot here, scalar multiplied to the vector u. Okay? So that tells us that we can think of an opposite of a vector as the same thing as the original vector times -1. Okay, we're going to stop there, and we'll pick up the discussion in the next video.